Everyone, round 2 of physics. So yeah, let's just start with a quick recap of what we went through yesterday. So we talked about the role of theory, big picture. What do we hope that a theory of deep learning might accomplish? We drew some parallels there with the role of thermodynamics, statistical physics in the case of physics. We looked at this in a little more detail and started fleshing out this dictionary of terms in statistical physics, terms in learning theories, show that really they're the same thing at the end of the day. And then I argued that physics, or especially statistical physics and thermodynamics, was a very natural language for intelligence. It's a more attenuated version of this statement. Today, we're going to focus on what we started to look at in the last part of that talk, which was phase transitions. So we're going to see a review of several examples of phase transitions in the case of physics. So we'll start with a very toy model that illustrates many of the key points, what first order phase transitions are, what second order phase transitions are, and it'll give us an intuitive sense of what's going on there. We'll look at the phase diagram of water, and finally move on to making a few claims about the Ising model, which is like the harmonic oscillator of statistical physics. I mean, physicists have what, 2 models. They've got the harmonic oscillator and Ising model. So what I'm going to argue today is that phase transitions are, at least qualitatively, pretty much the only thing that matters in our universe. Yeah, even though our world is continuous, it seems like, right? At the highest level, things are much more discrete than they appear to be at the microscopic level. And so phases separate these qualitative regions that we find this universe in. Okay, to get to that point, let's start simple. A little toy example. So I'm going to take you through the setup. We'll look at the first order phase transitions in this model, second order phase transitions. We'll talk about metastability and fluctuations. And then finally, we'll close with a little bit of math and some Landau theory calculations for what's going on here. Let's get right into it. So in this setup, I want you to imagine a cylindrical tube that we've rotated into a half pipe. Okay, and we put a little stopper thing in the middle, a piston that can move along this half pipe cylinder. All right, so it can move back and forth. But there's a vacuum here, at least not a vacuum, it's sealed off. So there's some finite number of particles contained in this piston that cannot leave. Okay, so what happens? What happens if you give it a push? Well, because this piston has mass, it'll want to come down as far as it can. But there's a force pushing against it, which is the pressure of the particles in this pipe. We assume there's a seal here. And so, at some point, these two forces balance out, and the force pushing back from pressure balances the decomposition of the gravitational force pushing that direction. And then there's some normal force pushing against the pipe that gets offset, for every reaction, it's an equal opposite reaction by the pipe. So it stabilizes, not quite at the middle. I mean, it could. The middle point is an unstable fixed point of this configuration, but if you hit it, it'll settle slightly to the left or right. Okay. So that's the question we're trying to answer here. At what angle does it settle? Where is it stable? Now, before we look at that example, we're going to look at a slight variation of this problem. So we're going to put 2 ball bearings in this pipe, one on either side of the tube. And these ball bearings will be made out of different materials. So they'll have different, what's the word I'm looking for, compressibilities. They'll respond differently. They'll stretch or, shrink depending on the temperature, but at different rates. And so if you plot what the radius is of these 2 balls, we start to make sense of what's happening with first order phase transitions. And so you see I've plotted these radii, and at some point, for some temperatures, the red one is smaller than the blue one, and at some point in the future, they they switch sides. And this should already remind you of the figures we saw this morning, where we saw so what do we call them? They're not learning curves, the free energy curves switch places. Okay, so what do we expect to happen here? Well, if this is bigger, then there's gonna be more pressure. There'll be less volume here on the left-hand side than on the right-hand side. And so that'll push the piston towards the right. It'll be more stable on the right-hand side than it would be on the left. And you keep increasing the temperature, and at some point this switches places. However, right, suppose I've started it on the left-hand side and I do this procedure. So now I'm increasing the temperature. At some point, the right-hand side is more favorable. Well, it's still locally the case that it's stable. So it's not just immediately going to jump over to the other side. So we'll look into that a little bit more when we talk about metastability. But in any case, what we see here is a first order phase transition if it were to change perfectly. So what I've plotted in these bottom three figures is the free energy as a function of the angle of this piston. So at first, when the red ball is smaller, it'll be most stable on the left-hand side, and I increase it. At some point, I get a perfect double well, and then the second double well comes down. And so this is a first order phase transition because it involves a discrete jump in where the stable point is, where it involves a discrete jump in the point that minimizes the free energy. Okay. So if you plot the angle that minimizes this free energy as a function of the temperature, it'll have this shape. It'll come down, at some point, discretely jump down. That's the first order part, the fact that there's a discrete jump. Yeah. So again, this is plotting out the same graphs on this graph now. Now let's look at the original example for a second order phase transition. We remove the balls and ask ourselves what happens now. Now, as before, you have this double well kind of potential, but now, there's no asymmetry in the wells.
The first order, if you go back, what exactly was the first order transition?
The first order transition has to do with the fact that you start here, you heat it up, and now you're still on the left-hand side, and you heat it up some more. And now if you want to end up in the most stable configuration, there'd be a discrete jump to the right-hand side. So there's no continuous deformation from here to the right-hand side.
So what exactly is the first order phase transition? The fact that a global minimum becomes a local minimum?
So, okay, so I wanted to come back to this in a little bit, but I can say it, right? So yesterday, I introduced a phase transition as involving a discontinuous change in the free energy, one of the derivatives of the free energy. So yesterday we saw that the free energy is this generating functional. By taking derivatives of the free energy, we can generate expectation values of any quantity of interest, anything that we could actually measure, because expectation values are measurements. So first order phase transition means it's in the discontinuity is in the free energy itself. Second order phase transition means there's no discontinuity, there's a kink instead. So the discontinuity is in a higher derivative than the original. So I think it'll make sense in a little bit. We'll get to comparing the graphs for the first and second order phase transitions. But let's look at the second order phase transition. And so this pipe, we've got the little piston, and now it's perfectly symmetrical on either side. So it could settle on either of these points. So now, again, I've plotted the angle where it would be most energetically favorable for this thing to sit as a function of temperature. Okay, so at first, for low temperatures, it'll sit on either side. But at some point, I heat it up, and it heat it up so badly that it's being pelted by impacts from all the particles on the left and right, and it'll balance out. And it'll push the piston towards the center of the pipe. So at some point, this quadratic potential flattens out and becomes something more parabolic. But at this critical point where this transition happens between quartic and parabolic, you have this critical point where the free energy is actually flat. It's like the example that Edmund gave us, this x to the fourth potential. So that's what happens at this critical point. So what we see here is that in a second order phase transition, right, this change is continuous. There's no sudden jump from one well to another. It involves a continuous change in theta. Okay, let's say something about metastability fluctuations. Right, so as I said, this is not quite a perfect example of phase transitions in physics, because this configuration will be very metastable. So if I push this piston to the left with the two balls, because it's now the most energetically favorable state, and I start heating it up, so at some point, the better state will be on the right-hand side. Well, you know, normal fluctuations, normal thermal fluctuations are not going to be enough to push this over the hump, at least if it's heavy enough. If it's very light, it's another matter. So maybe that's, you just like to think of a very small piston and ball where it's very light weight and the thermal fluctuations could do something like this. But in any case, we encounter this idea of metastability quite often, and we'll see it show up again in the case of fluids, in the case of, for example, supercooling. Okay. Yeah, so the question here to see like how metastable is it, how quickly does this transition happen, the phase transition happen, has to do with how high is this bump between the different stable points. If this is on the order of room temperature, then you expect normal thermal fluctuations to be enough to push the metastable state over into the true stable state. Okay. So now let's focus in on this part of the second order phase transition we just saw. So the high temperature region here. So as I said, you get this flat potential here. And what you should think of happening here is that in the case of the more parabolic shape, the slope here, the slope of the free energy tells you something about the restoring force. So it tells you that a small perturbation, a small perturbation away from that stable point will quickly be pushed back. If it's very flat, then a small perturbation will not settle back very quickly. And so what we observe with second order phase transitions in particular is that the fluctuations get enormous. Yeah, and then we'll see more about that later. Yeah, and so another thing to focus in on is what happens in this regime, the low temperature regime, or these two equivalent stable states. Yes.
Is metastability equal to local minimum of global?
Yes. Yeah. Okay. So, you know, the top of this piston, if there are no balls in there, if there are no asymmetries in the setup, is also stable. Is also a fixed point, but it's not stable, right? So an infinitesimally small perturbation to this model is going to push it out of this state. And so that's what we see here. So there's a dotted line showing that this is also a fixed state of the free energy, but you're never going to observe it because in nature we have thermal fluctuations. And so, you know, just one particle hitting it is going to be enough to perturb this. And this is something that we'll see again show up when we talk about spontaneous symmetry breaking. Okay, so yeah, fluctuations are important. They get really amplified at these critical points, at these second order phase transitions, and they ensure that we pretty much never see states stuck in these, you know, unstable fixed points. And so now let's compare first order phase transitions and second order phase transitions. I hope this clarifies for you, Alexander. Right, so for the first order phase transition on the top, it involved this discontinuous jump between the thetas, between the angles that were stable. And the second one, it involves this continuous change. Now, to some extent, the distinction, it can be kind of arbitrary because it depends on the observables you're interested in. And so, you know, like if you're looking at a second order phase transition, just take additional derivatives and you will get jumps. If you have a kink, right? You have something like this, well, and then the second order phase transition is gonna be nasty. This is blown up. So there's an equivalence here.
It's the derivative.
Yeah, so this is the original. If you have some observable that changes continuously, but there's a kink, so it's the second order phase transition.
Right.
Well, then just look at the next derivative and it's gonna blow up, or it's gonna have often some discontinuity. It could be something else. Yeah. And it doesn't necessarily blow up, it can just be a discrete jump.
So, but the first example is the global maximum shifts discontinuous. In the front. The second one, it merges to minimum. To one.
Yes. Yeah.
Is that how to think about it, or is that specific to these examples?
I think we'll see more about bifurcations in this fourth lecture.
I mean, in my head, it's the reason it's called a second order, it's always a discontinuous change in something.
Yeah.
And then whether it's the phase parameter or the derivative of the phase parameter or its derivative determines whether it's a zero first, second,
Right.
Yeah.
Sorry, the first, second, third, whatever.
Yeah. And then typically we just call everything above second also second. Like, yeah. Yeah.
So, mathematically, first one is going to do a critical value. Right? A critical point, map to the wire. Nothing happens about the configuration.
No, I'll point. So in the first row, if you take the critical points, so there's two local minima and then a local maxima in between them, and map them onto the f-axis, then you've got a configuration of 3 points on that f-axis, right? And as you move from left to right, first graph to second graph to third graph, the configuration of those 3 points changes, and actually 2 of them hit each other, right? Yeah. They interchange and they pass through each other.
Right.
But there's a point where there's only 2 values, right? Now, if you look at the second graph, it's the same. keep up, just. If you look at the second row, but now look at the critical points. So that's on the theta axis. You have 3, 1 for the 2 local minima, 1 for the local maxima.
Right.
But then as you move to the left, there's only 1.
I see. Okay.
So that's mathematically in stable maps, you'd think about the configuration of critical values and configuration of critical points. That's another way of thinking about
Right. Okay. So these nth order transitions and these critical points and like script. There. Okay. They're sort of corresponding.
And then like an important distinction between this classical example and thermodynamic systems is that in thermodynamic systems, thermal fluctuations are usually more than enough to break metastability. So you don't often see this case where the piston is still going to stay on the left hand side. It'll jump very quickly to the other side. Let's look at a little bit of math. Promise this is pretty much all of it for today. But what you can do is you can write down the free energy for the system, right? And it's going to have some potential energy term, and then the thermodynamic term, and this potential energy term is just the force of gravity times where are we? R cos theta gives you how far away this is from the sorry, it gives you the normal component of gives you the can't do math when I'm close to a whiteboard, of course. Yeah, it gives you the normal component to the due to gravity, and you have these 2 free energy terms from the left side, from the pressure pushing from the left, pressure pushing from the right. And so this you can just solve with a little bit of ideal gas law, and you work it out and you find exactly what the shape of the free energy is. And so in Landau theory, what we do is we take an expansion of the free energy in the vicinity of the transition. So we just do the standard thing that physicists always do, which is Taylor expansion. You take only the first two terms because that's all we can do. Like, I'm sorry, guys. This is like literally, oh, we're able to, well, in this case, 4 terms, fine. Everything else you throw out, and you end up with, predictions for where the critical temperature is, where the stable angle is as a function of the distance from the truth, because this is going to explain relatively well how your system behaves as long as you're close enough to that transition.
What is, oh my God, there's so many things. So F is
the free energy.
free energy, and somehow that is MGR. Okay, that makes
So
sense.
yeah, this is just like,
but then there's FL and FR. Oh, that has to do with the
yeah,
temperature.
it's the pressure you're experiencing from the left and the right.
Okay.
The
so
gas on the left and the right.
So here you're mixing sort of the more classical mechanics potential energy with like some
Yes.
thermodynamics thing.
Yeah, so this is actually important. Thermodynamics, the limit of taking away noise, taking away thermal noise, the question of finding the minimum of the free energy reduces to the question of finding the minimum of the energy. So thermodynamics reduces to mechanics when you take out thermal noise, which is nice. Right. Okay, so this is a simple example to prime your intuitions. Now,
So
let's.
I didn't have to understand all these equations, right?
No,
Just
it's just-
ignore them.
No,
Okay.
it's fine. Now let's go understand this entire diagram, right? All 10 solid phases of water. No, we're gonna focus on a little subset of this diagram. But yeah, so suffice it to say, water has a lot of depth, right? So we're just gonna look at that's so stupid. We're gonna look at just the normal phase diagram you get to see in a standard physics class. So we'll look at these transitions between solid, liquid, vapor. Yeah, so we'll focus on these transitions between, well, I just named them there. I'm not gonna read them out. I totally forgotten the word for deposition, so yeah. But there are names for all these things anyway. Right, in particular, I'm gonna focus on these points and take them one at a time. At the end of it all, you should have a pretty good understanding of what's going on in this diagram. So yeah, to emphasize the key points, here we're plotting temperature, here we're plotting pressure. So you see that for fixed pressure, say, 1 atmosphere, I move across this diagram. At some point, the solid turns into a liquid. And I keep moving to the right, and at some point, the liquid turns into a gas. And then depending on my pressure, things get weirder, right? So that you can have this triple point where things coexist. You can have this critical point where water and gas sort of show up as the same thing. Yeah, and we'll get through all of this in a second. Okay, so first we're going to focus on the transitions. So it's the blue and red on this diagram. Then we'll talk about metastability and fluctuations, just continuing this discussion from previously and show how it shows up here. We'll talk about what actually happens on those black lines, those coexistence points of different phases. And we'll talk about the question of divergence. And yeah, that's right. I got rid of like 2 extra points because I wanted to not make this horrible for you guys. So transitions, right? So here you see an example of first order transition in the case of water. And you should berate me for having hidden the axes. What I have plotted here at the bottom, it's no longer an angle. We don't have an angle of a piston to worry about here, but it's going to be some other quantity like the volume of the gas or the compressibility or some other property that is very different.
By saying you haven't labeled the axis, you mean you have a diagram which has axis, pressure, and temperature, but in that diagram,
Yes, I'm talking about
sub-diagrams.
Yes,
These
exactly.
don't have
Yes.
labeled axes. Okay. Okay.
So there are different things you could use to label this. The y-axis is going to be the free energy. just always. And the x-axis can be something like volume, or yeah, compressibility is another example. These are quantities
Right.
that will go through this.
So there's these macro observables.
Yeah, and in particular ones that, like looking at ones that differ between gas, liquid, and solid states. And so the second order transitions will be, if you look on this curve, you see that at some point they converge. This quartic becomes smaller and smaller, and you get this flat region at the critical point. So it's the same shape, it's just a different x-axis than before. Okay, so let's talk about metastability. Let's take a point, right above the boiling point of water at 1 atmosphere. There's this blue point right here. So I'm gonna, think about my gas and draw a kind of boundary around some small region of this gas, so that within this region, I have a fixed number of particles and I have a fixed pressure at the interface. And because this is in, hopefully the system has been running for a long while, it's small enough, this particle's in thermal equilibrium with the outside. So you remember I talked about walls yesterday as the thing being the thing we use to control thermodynamic systems. Well, here you see that walls are constructs, right? They're not always physical. Like, sometimes they're whatever we want them to be. Okay, don't take it too seriously. We're just, yeah, we're doing. Yeah. Anyway, this defines this MPT ensemble, so you end up again with a Boltzmann distribution in terms of these parameters. Okay. Yeah, and so what you'll see here is this is just the zoomed in version of the plot we already saw, where on the x-axis I plot volume, for example. And so one of these minima will correspond to the state that shows up in water, the other will correspond to the state that shows up in gas. And so the gas is lower in this point because we're above boiling point. So it's more favorable. But the fact is that, every so often, this little bubble can jump into the left-hand side, right? If it's small enough, there are fluctuations and it'll temporarily revert back into the liquid state. And so that process is slow, but the reverse process of liquid to gas is very fast, because this well is much, the height from the top well to the top is much smaller. And so what this means is that if you're looking at a gas like where we are, right above the boiling point, there'll be constant fluctuations where little droplets form, very temporarily, very, very tiny droplets before they evaporate back out of existence. All right, so that's just that point that we saw earlier. Okay, so let's look at this in a little more detail, talking about metastability. So just as before, right, we saw with this piston that if I increase the temperature and now this state is less favorable than before, you need thermal fluctuations to eventually push you over the top. And in that case, you don't see them necessarily. But in the case of thermodynamic system, you see those kinds of fluctuations show up more often. So what we've done here is we very slowly are cooling down the system. So each of these lines is an isotherm. It's a line of constant temperature. It's showing what the free energy is in terms of that. In truth, the free energy, we have it here, is a function of all three of those things we control: temperature, pressure, and number of particles. Here we're just focusing on lines of constant temperature, and we're varying. We're looking at how volume varies, right? So the question here, volume is unconstrained. So the question is, what choice of volume will our system adapt that minimizes the free energy? And so if you do this slowly, then it'll stay in that locally stable configuration and then eventually jump to the next because of thermal fluctuations. And so what you see here is the corresponding graph, where I've plotted on the right-hand side this figure that Dan sort of described before, where these are the locations of the minima of the free energy as a function of what do I want to say? Yeah, so those are the locations of the minimum of the free energy for these different volume types corresponding to those different phases. You see, at first, for very low volume, the gas stage is favorable. We push it past this line, and at some point it settles down. Now, in practice, this kind of metastability doesn't happen very often with the gas to liquid transition, but it does happen with the liquid to solid transition. So this is supercooled water, where you cool down water enough, and at some point you can flick it, and it'll create these waves of compression that then allow the water to solidify. It has to do with this. So in that case, you are, you're inserting external perturbations that allow you to push the system over this wall.
Keep a ball of water freeze.
Yeah.
Suddenly it freezes.
Evan.
My question is that those lines, those two lines, solid gas, those are sort of free energy of, say, solid at volume V.
Did I do backwards?
So my question is, what is defining solid here?
Did I just plot it backwards? I just did it backwards. Yes, it should be, yeah. Yeah, sorry, I just plotted backwards. I see them now.
Okay.
Yeah.
It's plotting on the right hand side is saying. So if you look at the left hand graph, so the marked red dots are in a local minima. Look at their heights. They change as a function of T, right? So that right hand potential well is the high volume phase, so that's gas. So gas as a function of T has a given free energy, that phase, and that's what's plotted in the blue line on the right hand side. So change the x-axis to temperature. Then at a given temperature, look at the gaseous phase and take its free energy, and then that's the graph. Yeah.
I think my question is, the other question I have is, why do we have three lines there? So in the previous example, we have the left and right phase. The minimum instant goes to left and right. Here we need something else so that there is a function that sort of given state tell you left or right before. Here we need a function that given state tell me whether or not it's solid liquid or gas. Is that
Yes.
is it just kind of a fancy? So
I
what
think-
Some values of the temperature. There are three phases, there's another local minimum.
Oh, sorry. So those three, right? So those three lines are corresponding to three of the local minimums.
Yeah.
Okay.
Yeah, and so like ideally you just stay along the bottom, right? Because then you're always in the global minimum. But sometimes you don't make that change immediately. Yeah, so like I said before, ignoring these x-axis labels can be different, but in reality, this is a surface. The location of these minima depend on not just one control parameter, but all of them. And so it's even possible to choose them in such a way that for some systems that all of the minima converge at some point. And that's what we see with the triple point of water. You engineer the pressure right and the temperature right, and you can actually see all three phases coexist at this very special point. Okay, so now let's talk about what's happening on the lines and look at this transition over here in the opposite direction. Yeah. Yeah, no, it's like, do you see like these require so much work? I didn't want to. I didn't want to change it anyway. Yeah, so first let's look at what happens as you move in this direction, right? So like temperature is actually something we measure. Like what are we physically doing we are bringing a hot reservoir in contact with the system. And so that the heat is leaking into the system, and that heat increases the temperature. But in fact, what happens, what you see is, if you plot the temperature of the system as a function of the heat that has gone into the system, it's not continuously increasing. What's the word for, I mean, this is still monotonic, but it's strictly monotonic. Okay. So at some point you reach this coexistence line, and the additional heat is going into changing the phase, is pushing it to the new minimum. And so that's what you see happening here, is it's being pushed into this new position.
Is that
Latent heat, yeah. Latent heat, in this case of, I don't know, at this point, is sublimation, latent heat of deposition. Like, this is latent heat of fusion. This is latent heat of
how much?
vaporization.
Like if I'm cooking water, just cooking, how much is that? Like, what is the order of magnitude of that?
Spend 1,000. I don't know why I have that on my.
I was about to ask. I remember, like,
I guess for freezing, most of the sort of freezing ice cubes cool your water is not because they're very cold, it's because of the phase. It depends, of course, on how cold the water is. It's minus 200 or maybe something. Because like an ice cube for your fridge, that effect from the phase is larger than the effect the temperature is from minus 10 to 0.
Right, because like an ice cube is like only a little bit colder than 0 degree, but I put it in and then it sort of absorbs.
Right, and yeah, then most of the heat gets absorbed.
All right, okay, cool.
and so, yeah, an important thing to observe is that the latent heat, I don't know, sublimation, is the same regardless of how you go through this point. So if I go through it vertically, it's also going to be the same value. And so that's what you see here. You know, here I've plotted a line of constant pressure. Here I'm plotting a line of constant temperature. And how are we controlling the pressure of the system while we're changing the volume? And so as I'm changing the volume of the system, well, at some point, you notice the pressure is no longer increasing as, yeah, it's no longer increasing as you make it smaller. It's just stable. At that point, the phase change is taking place and it's going into this new phase. At some point, it takes over again. Oh. Right, so if we look at this kind of from the side, then what you see here is a divergence in slope. So I want you to look at it at a 90-degree angle, I guess. And so we have these two concepts, the compressibility and the specific heat, which measure, you know, precisely how much this diverges, how much this curve is changing. Do you have them? They're flips. Oops. Specific heat, compressibility. Yeah, so dV, dP, constant T, and then yeah, that's divided by volume, so it still behaves the same. It diverges and doesn't go to. Oh, yeah, and if you plot these for the first order phase transition, it could look something like this. Right, so it's increasing. At some point, it jumps to. Okay, so another example of this I'm using here, symbol chi for susceptibility to hint at what we will talk about next. But at the critical point, often you see something more like this, where it's not just the discontinuity, you know, immediately at that point, but it diverges, it asymptotes already ahead of time. So yeah, we care about susceptibilities is a key part of what we will be talking about later this week. Susceptibilities are quantities that measure how sensitive our systems are to interventions. And so this is part of the reason that critical points are so interesting. It's because at critical points, systems are infinitely sensitive to perturbations. So even a microscopic perturbation, you know, a single atom tapping our system will change what configuration we're in, or yeah. So we'll talk about generalized susceptibility, right? Because susceptibility is usually reserved for magnetic and electric susceptibility. There are specific kinds of susceptibility to an external magnetic or electrical field. Here we're talking about sensitivity to any kind of external perturbation. We already saw compressibility in specific heat, so sensitivity to changes in pressure and temperature, changes in external magnetic field. And this is the kind of idea we have for the quantities we'd be interested in measuring for neural networks going through these phase transitions. Okay, and a small bonus. So notice that for water, the curve goes backwards. Now that's actually not very typical, right? Often it is the case that you apply more pressure to a solid, that's going to get more solidy, right? And here you see that you apply more pressure to solid, it turns back into the liquid state. That's because the solid state is less dense than the liquid state. And this is the reason, I mean, kind of turning around causality here, but this is the reason life exists. Because if water could not float, then it would sink.
I mean, ice would.
If you know what I mean. If ice did not float and it would sink, well then you would freeze the next layer of water. That would sink. You would freeze the next layer. And at some point the entire ocean would be frozen. Right? I mean, I guess life finds a way, but it would be harder. Yeah. Yeah. And the other reason is the other benefit of this is that it lets us ice skate. So at least that's like the explanation, right? You put pressure on water,
right,
and you get a little layer of on ice. God, you're doing it again. It's water, H2O, right?
Sometimes when you say water, you mean solid water.
Solid, exactly. That's all.
Solid water.
Yeah. All right, enough of water, right? Let's talk about the icing model or the Ising model. Okay, so the Ising model is as follows. It is ostensibly a model of ferromagnetism. So the justification for what's going on here is something like this. You have a magnet, and that magnet contains a whole lot of electrons. Those electrons have a spin, they point in a direction. And so the combined effects of all those things are to create this magnetic field for this magnet. So let's simplify things, right? Let's just say that these spins, the magnetizations of these individual particles, electrons, just point up or down, or binary. And additionally, we're going to look at a system where the only interactions are local. So these spins have a tendency to want to line up with their neighbors. That's what we see here in the Hamiltonian, the energy function. So it's favorable for two spins to be pointing in the same direction if they're next to each other. And additionally, there's some external magnetic field H, which pushes all of the spins to try to line up in that direction. Yeah, the question is, what do we observe? What are the magnetic properties of the whole? Yeah, so talk a little bit about spontaneous symmetry breaking, talk about scaling and finite size effects, talk about criticality and universality to end us off. Okay, spontaneous symmetry breaking. Okay, looking on the left-hand side, we see a curve that's very similar to the curve we saw at the beginning, the second order phase transition in case of this half pipe. So instead of plotting the angle, here I've plotted the magnetization, which is just the sum of all the spins. It tells you, what is the overall magnetization of this material. And so what we see is that as we increase the temperature, where in the Boltzmann distribution that this shows up, the temperature is going to show up. So 1 over temperature term in front of this entire thing. You increase the temperature, and at first, all of the spins are going to want to line up and they'll point either up or down. And at some point, they're allowed to fluctuate enough that there is no overall magnetization. And it's completely averaged out to 0. And you have the second order phase transition between those two regimes. So here are a few examples of what the system looks like at different points. So for low temperatures, you see these large regions, domains where spins line up. And at criticality, you have this fractal structure where you see fluctuations on every length scale. And then, you know, in the high temperature regime, it's just white noise. Okay, if we look at this part, right? Just as in the case of this half pipe, it could be the case that you have the spins in two domains that exactly cancel out. Two infinite domains that have one border between them, and the net effect of this is for the spins to line up in that direction. However, you know, this is not a stable configuration, and so even if I make one perturbation to this, you'll break that, and you will incline the entire system to magnetize in a particular direction. In the long time limit, so there's some discussion of metastability here, and this is the reason. Anyway, there's a lot to be said here, right? So, yeah. So, if we look closer, what do I want to say here? Just one second. Right. So, okay. So the magnetization is what we call an order parameter. There's a symmetry here in the theory. If you look at
external, no.
So H is this external magnetic field. So you can imagine activating H, and if H is really high, then all of the spins are going to want to line up facing upwards. If it's very negative, the spins are going to want to line up facing downwards. Yeah. So what you see here is that it takes an infinitesimally small H for this unstable equilibrium in the middle to be broken.
Your graph on the right side H.
Yeah, this is for H is 0. Otherwise, if H were not 0, then you would immediately see that one of these becomes favored. Yeah. So spontaneous symmetry breaking. The important thing to notice here is that this theory, at least for H is 0, has a symmetry. And that symmetry is that you can flip all the spins and it has the same energy. So it's this discrete symmetry. However, the states we end up in are going to be one of these two. It's not going to be this middle component where you can flip all the spins and retain the same state. So what we end up with is a place where the theory has more symmetry than the state we actually end up with in. And that's spontaneous symmetry breaking. And so what this is related to is the fact that, you know, for once in physics, we're not allowed to exchange limits. So normally it's fine. Normally you allowed to do whatever you want with integrals and limits. But what we notice here is that if I take the thermodynamic limit is taking the limit of system size to infinity. So that's n to infinity. And I take the limit of this perturbation, the small perturbation epsilon going to 0, then depending on the order I take those limits in, I end up with a very different overall magnetization.
Magnetic.
Yeah.
So it's like I have an external magnetic field and I do like.
Yeah. This is all like kind of hand waving. Epsilon would be like H. You can imagine, yeah. Yeah, the yes.
Oh, they only flip one spin.
That's enough.
Oh,
Well, okay, so that's what you see here, right? So on the left-hand side, I'm first taking the limit of epsilon going to 0, and then taking the limit of n going to infinity. And if that happens, well, then the epsilon is negligible, and then you start scaling up the system. And what you end up with is the magnetization will be 0 in this regime.
right. Okay.
It'll be in this perfectly balanced point. But if I take the limit of this perturbation going to 0 after I've taken the infinite size limit, well, then I'm going to get this overall magnetization missing out. Yeah, so we have these non-commuting limits, which are at the heart of what's going on here. Yeah. Okay. Yeah, so spontaneous symmetry breaking. You know, in physics, you see this Mexican hat potential, the Higgs field. It's like it's literally this, right? You just hit it very lightly, and that's enough to break the symmetry of the state, give the state less symmetry than the theory. So let's talk about scaling and finite size effects. Physicists love critical points. They love second order phase transitions. Why is that? Well, we already talked about the fact that these fluctuations grow very large. Now, Landau theory cannot explain exactly what's going on at these points. You know, it tells us that there are large fluctuations, but in fact, what we observe is that the order here is much greater than we would naively expect from Landau theory. And so you get these fractal structures where the sizes of the fluctuation are distributed across all possible all scales. It's this scale invariance going on here. Yeah. So the correlation length diverges. If you find that changing a spin here influences spins all the way over there or across arbitrary distances. And this is to say that an infinitesimal perturbation has infinite reach, which is part of the reason we care so much about this in physics, is because this is where the microscopic world interacts with the macroscopic world in the most obvious way, where we bridge between the two. Yeah. And so what you can study is how do these susceptibilities behave in the vicinity of these critical points? So yeah, as before, you have this, you often the tiny t, which measures the distance from the transition. And what you observe is that it scales according to a power law as you get closer. These are the critical exponents. And so there are a whole bunch of quantities. Susceptibility. Yeah, I think, I mean, we saw these three examples. I'll go back a little bit. These three examples, right? So susceptibility, like it sounds, it's sensitivity to perturbation, to a change in a control parameter. And so these are, when you go back here, you know, I had this chart. I'm going to do the direction. Right. So if the magnetization looks like this, and then this is temperature, and then this is the critical temperature, right? At this point, you look at the slope, and what is it going to be? It's going to be 0. And yeah, so the susceptibilities are often like the derivatives, the things that actually diverge at these points, right? Because, I mean, take a step back. So if you have, I should be more careful. Yeah, this is not necessarily this. If first order phase transitions involve a kink, if the phase transition involves a kink, then the next derivative is going to involve some discrete change. How do I want to draw this? Some discrete change in the derivative, because it has this kink here. Yeah. And then if you look at what happens here, that involves a kink in the next derivative. So there's always a discontinuity somewhere when there's a phase transition, which means there's always a divergence in the next derivative.
Why?
The way a physicist would say it. The way a physicist would say it is that these are derivatives of extensive parameters, V, Q, I, with respect to intensive parameters.
Right.
As a mathematician, you'd say that intensive parameters are derivatives of extensive parameters. So P is du dv, T is du ds.
Right.
So if you flip those things upside down and think about it, you'll see that those, you're differentiating something with respect to a derivative that's a second order derivative.
Yeah, because you can just flip it.
Yeah. Everybody knows.
Everybody does. Yes.
There's a question
Yeah.
from the chat as well. If we imagine this as a 2D random process, what model describes this fractal structure? Because the noise phase is obviously Gaussian.
I don't think I
That's
fully
applied
understand.
noise Gaussian.
No, I don't think I understand what the question is asking. What
Um,
model would describe.
yeah, I don't quite understand either. Imagine this as a 2D Gaussian process. So I think what it is asking is that if so this is a random function with 2 parameters. So in the noise space, this is just television snow. I guess he's asking in the non-noise
Oh.
space. In the noise space, it will be
Like
so what random process describe the fractal phase, because the correlation function for that
yeah,
random process will be highly non-trivial, right?
like how do you write down a random process you can sample from that generates pictures?
Yes.
I don't know, like just get a magnet and start sampling it. Of all, yeah, just do the physics.
Yeah, the
I don't
random
know.
process is the easy model. Critical.
Yeah. Okay. Yeah. So we'll say a little more about these critical exponents in a second. Another thing to observe is we already talked about this thermodynamic limit where n goes to infinity. And this is actually essential to get these true phase transitions we see in theory, right? Because physical systems involve finite sums of analytic functions. And finite sums of analytic functions do not give you divergences. Doesn't happen. You need infinite sums of analytic functions for that to happen. And so that's why like the true phase transition only happens in physics because 10 to the 23rd is basically infinity. It's closer to infinity than it is to 0. Yeah. Yeah. So what you observe is that it's going to spread out this distribution, and it's not just not going to be a perfect divergence, but often depending on the boundary effects of the system, it can move the exact maximum at this point. And this is important for simulations because you want to understand things in smaller simulations, and you size them up, and you look at how it changes as you size things up, and then you can make statements about the infinite limits. Okay, let's say a little something about criticality and universality. So in physics, there's this idea of universality. These critical exponents we observe and measure these things in the lab are often the same, like exactly the same for very different physical systems. So this was first observed, I guess, in the 70s. Around then, the fact that experimental physicists were just going around measuring these critical exponents for a bunch of different systems. And hey, it turns out they're exactly the same. What is going on here? And on the right-hand side, I've plotted an example of some of these exponents. So these exponents, alpha, beta, gamma, delta, they all correspond to a specific thing we care about, like the correlation length or the magnetic susceptibility or some other quantity of interest. And I think it's a conjecture, but for ferromagnets, what we observe is the only things that seem to matter are the dimension of the system, the interaction range, and the spin dimension. So what we observe with universality is the actual, not just qualitative, but quantitative behavior close to these critical points is the same. It depends only on a very small set of symmetry properties of the system. So close to these points, they have this fractal structure, and it constrains these systems even more than they usually are. And it ensures that the microscopics, like in some sense, don't leak through to the high level reality, which is kind of contradictory with what I just said, but just deal with it. Yeah. Yeah. And,
Big exception now that's topological.
Yeah, topological, we can talk about that another time. Okay. So yeah, so you end up with these observations like system that is, you try to write down a microscopic theory of magnets or some fluid or of maybe a brain, and they turn out to behave almost identically in this close to these critical points. So I mean, part of this, like this is starting to get at the reason that physics even works. Why it is that physicists are able to get away with such gross oversimplifications all the time, which just like should not be allowed if you didn't know better. And that is that our simplified models are in the same universality classes as the truth. And so they capture the essential information, and our universe is just organized in such a way that things behave nicely like that. Yeah. Now, yeah, I want to end on linking this back to neural networks a little bit. Right, so there are these observations of scaling laws where you see these power laws. You see that the performance scales with some exponent of the amount of compute or parameter count or data set size. So what's critical here? I don't know, right? But when we see this, our thoughts have to go to something like the critical phenomenon in physics. And so exactly what that relationship is not understood yet, but it's something we should continue to look at in the future. And then this is this idea of the universality hypothesis in interpretability. Is it the case that many different models, different architectures end up developing very similar representations internally, very similar internal circuit structures? Maybe. There's some good evidence for this from the vision models literature, but we don't know how far it goes for other kinds of models like language models. And we also don't know what the relation is between this and universality as we understand it in physics. Is there a relationship? I mean, they chose the same name, so must be, right? But in any case, there's more work to be done. Okay, so to review, we looked at this toy transition, a primer for intuitions about first and second order phase transitions, metastability fluctuations. Talked about expanding close to these transitions to try to understand what's going on. Talked about the phase diagram of water, and the same kinds of questions applied in a new context, a more physical thermodynamic context. And then we talked about the Ising model, started to talk about these questions of criticality, universality. We talked about generalized susceptibilities, right? Why these are an interesting quantity to look at, because it tells us how much control we have over the microscopic world from the macroscopic world. And that will be a key theme when we get to the plan and other parts of this week. Thank you. Any questions?
Yeah, thank you for another very interesting talk. I almost feel like I understand the physics. So the spontaneous, if I put on my alignment hat,
does this work automatically? Let's see. All right, does this work? It does? Perfect. All right. All right. Yeah, it seems to be this business way of talking about path dependence development of a system, whatever the system is. And is about an issue at the head. But it could be totally overdetermined. Well, part of it is solvable. Okay, I just mean like there might be parts where like it could go into, it could be trained during training. Or it could, it could be going into it. Or it could be full. But it's mostly on. It's there. Right.
Oh, so this is a question. So how dependent on it's just some choices.
Yeah, I mean, like, yes, the space.
that all these mobile teams are fairly interchangeable a priori. So there might be some symmetry between.
The reason that we turned it off. I mean, we're back online. People are still here.
Yeah, I don't know.
Yeah,
Questions that are asked.
we can continue this discussion going with the other people.
What's your answer?
God, I don't know, man. Are we? I think we're online.
Yeah.
Okay, did people hear the question or no?
Alex was rambling about. So, does it have a relation to spontaneous symmetry?
Whether spontaneous symmetry breaking explains football.
Yes. Next
Great,
question.
thanks. That's the question I wanted to.
I don't know.
Right, so I've also got a question. If you look at the phase diagram of water, it would seem to me that what we're really interested in sort of explaining the world around us is really the shape of the sort of the curve of the first order phase transitions. And the second order phase transition is sort of well, sort of mathematical interest, but that's not really the thing that determines the structure of the world around us, right? It's the exact shape of the curve rather than that there's a triple point and there's this other kind of weird singularity. Those are kind of trivial, right? In a sense.
Mhm.
What are your thoughts? Because you do seem to think that these criticalities are very important and something universal, but it seems to me that it's really first order phase transitions that are important, not the same.
Right, it depends. Well, I mean, I already talked about how, to some extent, like the distinction between first and second is kind of arbitrary. It just involves a discontinuity in some observable, and so it depends on the observable. I don't know a priori like how many derivatives we have to take of the free energy before we figure out what it is.
Right. So the reason that here I would tend to think that it's only the first order phase transitions are important are because the observables of interest are happen to be these ones that, oh no, this means it's liquid, this means it's ice, and therefore it floats. And the second order observables that we can think of are just not as important in this specific example. Is that right?
That's also because think of how many controls we have in the physical case. So we constrain the number of particles, the volume, maybe the temperature, the canonical ensemble, the canonical ensemble, and then we wait for it to reach equilibrium, and then it's in this max nth distribution. It's in the Boltzmann distribution with these values constrained because they're not allowed to vary. And so, like, because there just is not a lot of freedom in the system, there aren't that many things going on. The physical things end up being high up in the list of free energy derivatives.
I have a question.
Yeah, I think that's a good point, but water is a very different kind of system to a brain or an AI. So like if you take a generic system, maybe its critical points are, as you say, like some points in phase space that are very unlikely to be encountered. But if the system is somehow driven by optimization or some sort of other incentive to use the physics that's available at the critical point in some essential way, then you won't be surprised to find it at a critical point. And that's the argument for why critical phenomena are relevant in the brain. For
Right.
example, like there's certain information processing advantages to being at a critical point.
Don't spoil tomorrow.
So I think that's right
Yeah.
for many physical systems. But we do have good reason to think that for certain classes of systems, that they will be preferentially found in points near the critical point. Yeah, but that's a good observation.
There's a technical question in chat. On slide 67, the symmetry breaking, the limit, I think, so the limit, the commutativity of limits, if I remember correctly. So the question was whether or not the quantity on the right hand side should be plus minus one.
Yeah, so there should be a
depending on the sign of the epsilon.
Yep. Plus.
Sharp audience.
Yeah.
Yeah.
Sarah's in the audience. Well, maybe I want to. So the question I had is, could you try and do the lecture yesterday and tell a little story about what is water and what is ice and stuff in a neural network? What would this correspond to? Or what would these? I remember you said something about batch size and like something. I don't know. Tell me.
Were you there for Dan's talk this morning?
The phases are actually these platonic solids. Is that not real?
Well, they're not actually solids. Shapes.
Right. Okay.
There's a question about symmetry breaking. Can you just say it one more time? Oh God. Why did I do this? Okay. So like the important thing is to look at the theory, right? This Hamiltonian fully describes what's going on in the system. And this theory, if I take H is 0, this term vanishes and I'm only dealing with the first term. And now if I flip every spin Si at the same time, the two negatives just cancel and I get the same energy. So the Hamiltonian is the same for bold S and minus bold S. However, the state we end up with which is going to be inclined to all be facing up or all be facing down. Bold S generally is not equal to minus bold S. So the state has less symmetry than the describing theory. And that's spontaneous symmetry rate.
The direct answer to that question is like, is it plus or minus one is a breaking, but I'll say it's yes, like the fact that we fall into one of them.
Yeah.
But the observed is one of them.
Yeah, but let me see. I suppose
One of the limits doesn't exist.
Yeah.
One of the limits exists. The other one doesn't exist, but you could think of it as being possible.
Yeah.
I don't know if that's profound enough to repeat, but the point would be that it's neither one nor minus one. It's just that limit on the right hand side doesn't really exist, I would say. So the limits don't commute because one way it exists, the other way it doesn't exist, but not because 0 is not equal to 1. I would think that this is not something I'm very familiar with.
I think the question also, if you take the limit, the one-sided limit as epsilon goes to 0 from the positive direction, then it is 1. But if you take it from the other side, then it is -1. And that is the kind of the definition of limit doesn't exist because it depends on path. So that's exactly what Dan said.
Yeah, maybe let me just say something more. When we talk about symmetry breaking, we're talking about the facts that real symmetry break is the -1 plus 1. The symmetry breaking is the fact that, you know, if we start out up here, like we never stay there, and so we end up falling into either one of the two. I guess the answer to the question is yes.
Yeah.
No. We're into there. Cool. See you guys in 40 minutes.